First, we introduce two mathematical functions. One is called div, the other is modular. And div here, of course, represents divided by. But when we do 9 divided by 2, and when we have this function divided by, we only look for the quotient. So 9 divided by 2 has a quotient 4, because 2 goes into 9 at most 4 times. It also has a remainder 1, but we will use it as an answer for 9 modular 2. So MOD represents modular, which is a function looking for the remainder. And we know that any integer divided by another integer except 0. For example, 247 divided by say 16, we can always get a quotient and a remainder. And the remainder, we always want the remainder to be smaller than 16, because if it's bigger than 16, then we can continue. So for example, here 16 goes into 24 one time, and we do subtraction, we got 8, and bring down 7, we got 87. And 16, we figure out 16 goes into 87 how many times? So if we put 4 times, we get 64, and when we do subtraction, we still get 23. And 23 is bigger than 16. That means 4 is not big enough, so we need to increase it to 5, and we get 80. And 87 minus 80, that will give us a 7. Now remainder is smaller than 16. So the remainder is always less than or equal to, I'm sorry, not equal to, less than the divisor. Because even if it's equal to 16, we can still increase the quotient by 1. And also, we always want our remainder to be positive, because even if it's a negative, we can negative 247, we can still divide it by 16, and we can get a negative quotient. So we want the quotient can be negative, but we want our remainder to always be at least 0. So if we divide 8 by 2, then we will get remainder 0. And so the remainder is at least 0, but it's always smaller than the divisor. And so by this observation, we get these two properties. Any integer divided by 2 has 2 remainders, either 0 or 1, because the divisor is 2. So either the remainder we know is always going to be smaller than the divisor. So and at least equal to 0. So all we get will be the number, the whole numbers less than 2 will only be 1 and 0. And similarly, any integer divided by 3, that's the divisor, and the remainder has to be smaller than 3, so it has to be 2, 1, or 0. And the reason we talk about this is when we're going to divide all the integers, positive or negative or 0, into we can divide integers into different categories. So if we divide an integer by 2, we get either remainder 0 or 1. If the remainder is 0, that tells us this number 2 goes into that number, which means this number is multiple of 2, which is the even number. And if the remainder is not 0, it's 1, then we know that 2 does not go into that number, and that has a remainder 1, which means this number must be a multiple of 2 and plus 1 or minus 1. And so in this case, we can divide all the integers into 2 categories, 2k or 2k plus 1. Of course, k here is an integer. And this is what we talked about before, the case positive integers and negative even numbers or odd numbers. And if we divide integer by 3, then we will get 3 remainders, which means 0, and that's a multiple of 3, and 1, that's multiple of 3 by 1, and if the remainder is 2, that means the number must be a multiple of 3 plus 2. And so we can divide numbers into all the integers into these 3 categories. Either this number divided by 3 has a remainder of 0, which means 3 goes into that number, so that means then that integer is a multiple of 3. If 3 does not go in there, and leaves us a remainder 1, that means the number is a multiple of 3 plus 1. And if the remainder is 2, then that's a multiple of 3 plus 2. Okay. In a similar way, we can extend this and generalize this. If we divide a number integer by 4, then we get 4 remainders, 0, 1, 2, 3, and we can divide numbers into different categories. So the reason we talk about this is sometimes when we do the proof, we might need to prove the problem by different cases. And so later, next, we're going to look at an example. We have to consider case by case to prove the statement.